Hello everyone, this is Jennifer Nesta and we are here to discuss about bioremediation, which is part of Unit 4 in course code MIC 3732, Environmental and Agricultural Microbiology. So this particular topic will be dealing in two different parts. So the part 1 deals with different bioremediation or biodegradation mechanisms, and in the part 2 we'll be dealing with bioremediation techniques. So shall we begin? Okay, so now we'll begin with discussing what is bioremediation. So as you already know, it is the use of microorganisms to degrade different contaminants. So obviously there are two questions now. What kind of organisms do we use, and what are the different contaminants, and what is contamination? Obviously, so bioremediation, it is not only microorganisms that you use. You can use any kind of biological means to degrade various pollutants. So the contaminants are nothing but the substrates and the substances, which we can also call them pollutants, which are capable of causing pollution to the environment. So according to EPA environmental law, pollution is defined as introducing a different substance or energy into an environment which will endanger the health of living organisms, interfere with the ecosystems, or interfere with the working of an environment. So it can be any contaminant that interferes with the workings or the basic law of nature. So these contaminants can be inorganic, they can be organic. So we already know what inorganic and organic are. Organic are any compounds that has carbon, hydrogen and oxygen in them, and inorganic are all other elements which do not have hydrogen and oxygen in combination with a carbon skeleton. So ultimately, this particular pollution that we cause, or what the release of a contaminant cause, this needs to be remedied. So usually pollution occurs in different biological resources such as soil or water, and of course air. So when we use a particular technique to remedy the pollution that has been caused to the environment, you call them environmental remediation. So usually we have treatment plants which are in situ, which are ex situ. We apply certain kinds of techniques to remediate the particular pollutant that has been already introduced. And all these mechanisms together are called environmental remediation. It is generally not bioremediation alone. We have other physical and chemical techniques. But when that means used is biological, when it is a living organism or a dead biomass that we use, then that particular type of remediation technique is called as bioremediation. So the next question that we have to deal with is the difference between biodegradation and bioremediation. So usually these two terms are often used interchangeably. We say sometimes biodegradation and we say sometimes bioremediation. Normally the particular meaning between these two words or terms are not exactly clear. So, but that is a very vast difference between biodegradation and bioremediation. And what is biodegradation? It is the breakdown of organic contaminants. So as we have already said, contaminants are of two types. They are organic and inorganic. Usually, when organic contaminants are broken down, when they are decomposed, and especially due to microbial activity, it can be due to other parasitic or protozoan organisms, or plant and nematode also. But usually, when microbial activity causes breakdown of pollutants, we call them biodegradation. So let's see in detail what are exactly the difference between bioremediation and biodegradation. So the difference between biodegradation and bioremediation. So biodegradation, as you can see, it's a very natural process that occurs in all cells. So the difference between biodegradation and cellular respiration is not much. So most of you are already familiar with cellular respiration, which is taking in a sugar, breaking it down with the enzymes. For example, starch with using amylase, and you convert it into monosaccharides. You take it as glucose. You bring it into glycolysis process, and you go take it into Krebs, and you take it into electron transport chain. You convert the whole molecule into bundles of ATP and electrons which are supplied to electron carriers. So the whole process is very, very similar to biodegradation. Biodegradation applies the same mechanism. It happens in almost all cells, but here the pollutant or the organic matter is very, very difficult to break down. It has something called as biochemical recalcitrance, which makes it very difficult for the bacteria or the fungi to access the molecule, and it has to generate a lot of extracellular enzymes. So this is a particular process which is common to most of the cells, especially microbial cells, and this process is again very slow. So it is primarily decomposition of materials. So the difference between biodegradation and bioremediation is this. Here in bioremediation, we take microorganisms which are capable of biodegrading among other methods. So there are different methods of how a microbe deals with a pollutant, organic or inorganic. So we take microorganisms which are capable of bioremediating, of biodegradation, and we apply it to a polluted site. We use it to clean a polluted site, to break down environmental pollutants, and we engineer it. Are enhancing it metabolically or deliberately introducing new microorganisms into a polluted site. So this is the difference between biodegradation and bioremediation. We are applying biodegradation capacity of microorganisms to a treatment plant where we enhance the whole mechanism. So because it is enhanced, it's very, very fast, and it is very intentional also. So biodegradation and bioremediation are two words which cannot be used interchangeably, and because it means two different things. So let's go to the next slide. Okay, so here again, bioremediation has three different things that are heavily involved. So obviously the first one is a pollutant, and the next one is the environment where the pollutant is present, whether it is soil or air, and of course the organisms. So what is bioavailability? The terms that connect these three factors of bioremediation are bioavailability, biodegradability, and physiological requirement. So bioavailability, as the word says, it is how much this pollutant is available in the environment to a particular cell. And it depends on the water content of the resource. So whether it is dissolved in water, whether the contaminant is present in water, whether it is dissolved in water or it is precipitated in water, whether it is present in soil, whether it is present as an ore, or whether it is present as in solid phase, in liquid phase, in gaseous phase. So that decides how much of the pollutant is readily available for biodegradation. And of course, we have discussed what biodegradation is. So how far can an organism biodegrade this particular pollutant? Can it completely mineralize it to carbon dioxide, or can it partially hydrolyze it? So that is the biodegradability or biodegradable capacity of an organism and the biodegradability of a pollutant. And the physiological remains that requirements that we already know. An organism is adapted to a particular environment. It needs a certain pH, an optimum level of pressure, temperature, carbon dioxide, a redox potential, a whole lot of factors which require the organisms to have optimum metabolic growth. So these are different factors and different concepts that determine how we can set up a bioremediation plant. So of course, biodegradability depends on the structure of the pollutant, presence and absence of enzyme by organisms, and bioavailability, the effect of limited water solubility and sorption rate at which a contaminant is taken up by a microbial cell. Okay, sir. Again, we are saying that there are different concepts to develop a bioremediation mechanism, which are what kind of pollutants we are dealing with, what kind of organisms that you have to induce or activate or provide, and what kind of techniques we have to apply. So under substrates, we have already discussed that a pollutant or a contaminant can be of two types. There are organic and inorganic. So according to EPA, that is Environmental Protection Agency, organic pollutants are called as POPs, which are persistent organic pollutants, and inorganic pollutants are called as inorganic contaminants, IOCs. So similarly, so in later slides, we'll see what these different pollutants are in depth. So similarly, there are different kinds of organisms that you can use. So you can use fungi, we can use bacterial cells, and we can also use plant, which is phytoremediation. And obviously for composting, which is again a decomposition technique, we use earthworms. So we can use different kinds of organisms to remediate an environment. Similarly, we have different techniques. For example, it is in situ and ex situ. So the sample, whether it is water or air, we can take the remediation to the polluted site. So we can build a plant there, we can set up, we can introduce an organism there by some means, or other than that, we can take the sample from the area, take it to a particular treatment plant and treat it there. So that is called as in situ, whereas when you take it to an external place, which is called as ex situ. Okay. Now, organic pollutants, as I said, according to EPA, it is called as persistent organic pollutants. And as you can see in the table, you can see that there are different classes of contaminants. So you can see that there are chlorinated solvents, polychlorinated biphenyls, chlorinated phenols, BTEX, which is your organic solvents such as benzene, toluene, xylene, and you have polyaromatic hydrocarbons, which is your naphthalene and your anthracene. And of course, we have pesticides. So as you see in this class of contaminants, or in this table, you'll be able to notice two different things. First of all is certain organic pollutants are byproducts of an industry. So for example, polychlorinated biphenyls are produced intentionally for agriculture. Okay, so other than that, certain other chemicals such as dioxins, they are not produced intentionally, but as a result of a particular industrial process, these are released as part of water or as dumped into soils or landfills. So organic pollutants can be generated through two different means, which is intentional production and unintentional production. Okay. Then the one more thing that we have to note is most of the organic pollutants are new substrates that we introduce into environment, and certain organic pollutants, and for that even sometimes inorganic pollutants, are something that is already present in nature. So we'll see what is the difference between them in the next slide. So inorganic pollutants called as IOCs, and these IOCs, as you see in this table, they're arsenic, cadmium, chromium, copper, mercury, nickel, lead. Okay, so these, as you observe, they are elements, normal metal ions, which are already present in the environment. So we have these elements in your periodic table. They are present already in the soil in forms of rock, ores, mineral substrates. So these at normal concentrations do not cause pollution. So arsenic and cadmium and copper are present in very, very low concentration in soils and in water as cations and anions, as positively charged ions and negatively charged ions. They're already present in nature. So in such concentrations, they don't affect life. They are essential. Some of them are essential trace elements that are even required for life. For example, our cells have certain enzymes which we call the metal enzymes. They need zinc and manganese and copper and nickel as cofactors. We need them, and we need the best example is iron. We need them in heme to act as ligands. So there are some of the elements that we need in very low concentrations, but due to industrial exploitation, these elements are sometimes dumped into water resources or soil resources in very high concentrations, and that's when they are called inorganic contaminants. So they are natural elements and compounds found in nature, but when they are present in toxic concentrations, they affect life. So this is a particular concept that you have to understand when you look at pollutant. For example, if you take plastic, which is an organic pollutant, was created or invented by man. This particular polymer, organic polymer, was not found in nature, but we created that substrate. But these days, what we have been observing is that microbial cells, fungi, and bacteria are capable of breaking down these substrates, even though these polymers are new to them, that they have not been in nature before, that they are introduced newly. They have this biodegradation capacity to evolve and adapt and produce enzymes that can break down these organic polymers. And at the same time, contaminants such as cadmium and arsenic are already present in nature, and microbes are already familiar with them at very low concentrations. So when they become toxic at higher concentrations, they develop again new mechanism to deal with them differently. So next we are going to look into what are the different kinds of mechanisms or microbial interactions and how they deal with different organic and inorganic pollutants. So this is a very beautiful illustration from Nature Review. It shows how different microbial cells deals with different pollutants. Not pollutants, different materials that are commonly found in nature. So these are mechanisms which are very common in different cells. So these are not very specific to pollution, but they are common mechanisms of cells that they use when they deal with organic materials, rock or mineral based substrates, or metals and alloys. So as we see in organic materials, we can see that the mechanism they perform is biodegradation. So when organic pollutants are when the cell encounters an organic pollutant, it produces biofilm. So that is one of the first things that they do, and it is very common for a cell to produce biofilm in case of rocks and minerals, and also in case of metals and alloys. So this is a common mechanism found in cells when they deal with metals, when they deal with organic pollutants, when they deal with plastic, when they deal with the wood, when they deal with pesticides. So whatever may be the pollutant, usually microbial cells, bacterial cells find themselves forming biofilms because it makes them very resistant to toxicity of the pollutant. So the first steps that they usually form is forming a congregation of cells, which we call the biofilm, and the next is obviously forming extracellular metabolites, enzymes, which ultimately decompose them into carbon dioxide and oxygen and water. So and at the same time, in when they deal with rocks and minerals, so as I said, an organism needs iron, nickel, copper, which are trace elements, in very low concentrations. So they have to find these metals from soil or from water, and when they meet a rock, which is a very hard substance, they have to weather the rock into powdered form, that is break down the rock into very soft soil particles. So that particular process is called as weathering, and this can be two types. This can be done in two types. The first one is physical, and the next one is biochemical. So biochemical is usually producing organic acids. So these organic acids break down the rock, and when water enters these broken down rock particles, they leach these metals into the neighboring soil. So that is one way of how a cell does bioweathering. And the next type especially by filamentous organisms. So like a plant has roots, how it is able to break down our compound walls, concrete walls, filamentous organisms such as actinobacteria, fungi and algae, filamentous organisms usually tunnel the rock particles and break them down, and then they penetrate and absorb the metal ions from the mineral substrates. So these are, of course, there are different kinds of humongous amount of mechanisms by which they take this mineral content. But these two methods are one of the most preliminary mechanisms by which they access metals under normal conditions, but not in polluted conditions. So similarly, when they meet metals and alloys in nature, the procedure that they undergo is biocorrosion. So certain bacteria like sulfate reducing and nitrifying bacteria, they precipitate this particular metal out, and for that they do biomineralization or biocorrosion. Again, you can see that formation of biofilm and EPS, and one particular technique called as metal complexation, that is compounding the particular element from ion form to compound form using redox potential, is one way of how they deal with metals and alloys when they face it in nature. So these are some of the basic mechanisms of how a microbial cell encounters different materials in nature. So we will see in depth what are the different types of biodegradation and what are the different types of bioremediation of metals. So it's a very short glossary. You can take your time and go through it. So what is bioweathering, biofouling, all are given in very short forms. You can go through it later. Okay, biodegradation of POPs, persistent organic pollutants. So in case of biodegradation, there are primarily two types of substrates. So pollutants, as we know, they can be polyaromatic hydrocarbons or pesticides. Microorganisms, when they break down these complex compounds, they deal it in two types. First is they consider them as primary substrate, where the particular pollutant acts like a sole energy source. So as you see in the diagram, this is your primary substrate utilization. So you can see your microorganism and the carbon source, especially glucose, which is a very important carbon source we need for our respiration, and they form carbon dioxide and H2O. So this is normal mineralization process. This is how our cell works. This is catabolic mechanism that happens always in our cells. So you need a carbon source, you need an energy source, you need essential nutrients, and you need oxygen. We call this whole process cellular respiration. So this is how a cell deals with an organic pollutant. And that process is called as primary substrate utilization. We can also call it complete biodegradation and mineralization. If we have to call it complete, it should be producing carbon dioxide and water. So our pollutant, instead of glucose, if we have pesticide, the pesticide complex should be completely broken down to carbon dioxide and water, and it should generate ATP. So that is the concept behind the primary substrate utilization. So in primary substrate utilization, the first step, most usually the first step, is production of an extracellular enzyme. So you can see how alkanes, which are common organic components which are found in your organic pollutants. So we can see what are the different enzymes they produce, how they convert it into carbon dioxide and water. So we have alkane here. We have two different types of enzymes, monooxygenase and dioxygenase, and ultimately they are converted into fatty acids. So they undergo, the enzyme subjects this pollutant into a complete set of chemical reactions, and we have fatty acid, and this fatty acid is taken inside a cell, and we know how a fatty acid metabolized. It is converted into acetyl coenzyme A, using beta oxidation. So this acetyl coenzyme ultimately takes part in the pyruvate cycle, in Krebs cycle, and we have energy. So it is completely mineralized into carbon dioxide and water. So this is how primary substrate utilization occurs. The pollutant, organic pollutant, is treated just as a glucose is treated by a cell. The only difference is they produce very specific or sometimes non-specific extracellular enzymes which make the pollutant more biodegradable, more bioavailable for that matter. So the next method of how a biodegradation occurs by a microbial cell is secondary substrate utilization. So in the secondary substrate utilization, the cell does not derive energy from substrate breakdown. So if you see in primary substrate utilization, the material is converted into a form where it is taken to our metabolic process and energy is derived from the particular breakdown. But in secondary substrate utilization, the microbial cell does not depend on the pollutant for energy or carbon. They don't want to produce ATP, they don't want to get electrons from the breakdown, and they are not concerned whether it is involved in their own metabolic cycle. So they produce an enzyme which can break it down. Okay, so in this case, in the diagram, if you see, a particular organism, aerobic organism, has an enzyme called as monooxygenase. So this monooxygenase is able to break down the cell and introduce an oxygen. So in primary metabolism of that particular cell, it is able to convert isobutene into isobutanol, right? That is a primary metabolism. So this cell will take isobutanol and convert it into carbon dioxide. But in secondary substrate utilization, this enzyme also converts trichloroethene, which is an organic pollutant, and it converts into epoxide, and this epoxide cannot be used for metabolism. It cannot be converted into an organic form or taken into glycolysis or Krebs cycle. It cannot be used to produce energy, and this oxygenase enzyme converts this TCE epoxide just because it can, not because it needs energy from the particular pollutant. So this particular mechanism is called co-metabolism, and this epoxide is not mineralized into carbon dioxide and oxygen. It is an incomplete degradation. So this partial oxidation of substrate is called as co-metabolism or secondary substrate utilization, because it does not depend on this particular pollutant for energy or ATPs. Okay, so the third method by which a particular microbial cell deals with an organic pollutant is reductive and hydrolytic dehalogenation. So most of the organic pollutants are called persistent because they have an halogen such as chlorine or bromine or fluorine. So these halogens, because they are inert, they make it very difficult for hydrolysis and breakdown. So a cell, what it does is it produces certain enzymes where it introduces H2O, water, or introduces oxygen to remove the halogen. So if there is chlorine, it introduces hydrogen and removes the halogen, which is called as reductive halogenation. And if that particular halogen is removed by OH, it is called as hydrolytic dehalogenation. So once the halogen is removed, it becomes a metabolite which is easily accessible by the cell. So for example, we have here dichloromethane, which has two chlorine atoms, and when it is hydrolyzed using water in the presence of an enzyme, it converts it into formaldehyde, which is an molecule, an aldehyde, which is easily dealt with by the cell. Similar, and produces HCl. Of course, in cultures the pH may go high. Very low. So again, you have dichloroethane, which has a chlorine molecule. In presence of oxygen, the chlorine is removed to give you glycolic acid, And now this glycolic acid is a sugar acid. It is present in sugarcane, and ultimately they can be converted into glucose, or they can be converted into pyruvate and taken into the cell for biodegradation. So this conversion or removal of halogen using water or using oxygen and turning it into a sugar molecule or a sugar acid is called as dehalogenation. And there are two different types of dehalogenation, which is reductive dehalogenation and hydrolytic dehalogenation. So there are three different methods by which a cell biodegrades an organic pollutant. First is primary substrate utilization, where the pollutant is completely mineralized into carbon dioxide and H2O, and it produces carbon and energy source for the cell. The second type is secondary substrate utilization, where you have two methods, which is co-metabolism and reductive and hydrolytic dehalogenation. So in co-metabolism, there is only partial hydrolysis of the organic compound, and it does not generate energy or carbon source for the cell. It is just a byproduct. And in dehalogenation, because of the presence of halogens, certain organic compounds become very, very persistent in water or soil. So removing halogens using the water or oxygen, in the presence of oxygen, into sugar acids or simpler molecules is called as reductive and hydrolytic dehalogenation. So these are the three methods in biodegradation of organic pollutants. So in the upcoming slides, we'll see how microbe deals with metals. How do they deal with metal toxicity? Okay, so far we have discussed the different mechanisms of biodegradation, of how a microbial cell deals with organic pollutants. And now we are going to deal with how a microbial cell deals with inorganic contaminants. So as we have already seen, inorganic contaminants, or otherwise known as IOCs, are primarily metals. They are made of elements which are toxic in low concentrations, such as heavy metals like lead, cadmium, and mercury, and certain trace elements which are necessary for the metabolic process of the cell, and but turn out to be toxic to the cell at very, very high concentrations, and they demonstrate metal toxicity. So as you can see in this diagram, there are the different mechanisms through which a metal element enters the microbial cell. So this is your plasma membrane, and these are your different methods through which a metal will diffuse or get pumped into the cell. So these are all protein channels, or transport proteins, which are usually involved in the transfer of substrates such as glucose or glycerol to the cellular matrix. So as you can see, lipid permeation is, as you know, your plasma membrane is a phosphobilipid layer, and it has a particular net hydrophobic charge, and it will allow only lipid soluble molecules. So metals which have a charge, a lipid toleratable charge, will be allowed to diffuse passively inside the cellular matrix. So such anions and cations will not have a problem. But other than that, we also have endocytosis, where it is transported into the cell through the membrane budding, and we have ion channels, ion pumps, and permeases, which are complex permeated proteins, membrane proteins, and carrier proteins, which help in active transport. That is, they spend energy to get the metal transported into the cellular matrix. So what happens to this metal once they enter the cell? So when at high concentrations, so as I said, these metals, some of these metals are needed for the cell at very, very low concentration, sometimes in nanograms. So when they increase in concentration, the cell will face severe toxicity problems. It will inhibit, as you can see here, it will inhibit cell division and their metabolic processes. So what kind of disruptions do they face? So the first one is cell membrane disruption. So especially if we know that metals like mercury and cadmium and chromium hexavalent, which are of course carcinogenic, and these can lyse our membrane proteins, sometimes our membrane lipids, and cause cell membrane disruption. So of course, they inhibit your protein synthesis at various levels. They can inhibit your transcription, they can inhibit your translation, and of course, they can also cause DNA damage. They can cause mutations in your DNA. And other than that, they can cause cell division, they can affect the meiosis and mitosis. In bacterial cell, they can affect your binary fission, and they can also act as an anti-metabolite. So that is, they can competitively inhibit an enzyme so that your metabolic processes are inhibited. And of course, the last thing they can do is denature a protein. Just like they affect our cell membrane proteins and their lipids, they can, once they are diffused or actively transported inside your cell membrane, they will denature certain proteins that they can bind to. So these are the different toxic effects that you can observe in a bacterial cell due to the exposure of inorganic contaminants such as lead, cadmium, mercury, nickel, zinc, and copper. So, and but that does not end here. And a microbial cell, which is very, very versatile and known for its microbial diversity, will definitely and has already developed various mechanisms of resistance. So, if the effects that are faced by the cell which inhibit cell division and metabolism is called as metal toxicity. These mechanisms are known as metal resistance. So in the next slide, we will see what are the different methods of metal resistance. Okay, so there are lots of methods that a microbial cell has evolved to detoxify the harmful metals. So what are these mechanisms? So from this particular diagram, you may know the different kinds of mechanisms. These mechanisms are practically divided into two, which is metal dependent and metal independent. So metal dependent mechanisms of resistance are very specific to a particular set of metal. For example, if let's say a particular reflex pump is specific to cadmium, it does not efflux mercury. So these kind of mechanisms which are very specific to a metal is called as metal dependent, and certain mechanisms that are common for all metals. So they will stop these metals from entering the cell up to a limit, and these are not at all specific at all. They are very, very non-specific. They will stop any metal from entering the cell. So what are these metal resistant? So metal independent mechanisms are many. There are lots of metal independent mechanisms, but these are the certain mechanisms that are commonly observed in microbial metal resistance. So they are EPS sequestration, siderophore production, and production of biosurfactants. Okay, so EPS sequestration, EPS stands for extrapolymeric substances, extracellular polymers, and extracellular polysaccharides. So when we are very specific, they usually mean extracellular polysaccharides, but when a cell, as we saw in the earlier slides, we know that when a microbe comes into contact with the substrate, a recalcitrant substrate which cannot be accessed easily, which is not available readily, they form biofilms. So EPS are components of biofilms. So biofilms are a congregation of cells which has extrapolymeric substances generated in a lot of volume and form a bed-like structure. So these extracellular polymers, or exopolymers for short, are very, very efficient in binding heavy metals such as lead and cadmium and uranium. And these polymers are negatively charged. So the metals which come in contact with the cell have to be ionized. So certain metals, whether they're oxyanions or cations or anions, their ionization is very dependent on its pH. So the pH dependency is taken care of by the extrapolysaccharide. So once the concept behind EPS sequestration is very, very simple. It is like your cell wall. It is a bed of molecules which is very, very thickly packed with the carbohydrates and fatty acids and sometimes of many times proteins, and they are primarily slime. They have the slime-like consistency, so they act as a bedding which immobilizes the metal. So it results in metal immobilization. So as you can see in this diagram, you have a complete bedding around the cell, the blue color structure. So they are in a complex matrix which forms around the cell, and they immobilize the particular metal from and prevent them from moving across the plasma membrane. So the concept is very simple. So when they deal with a very high concentration of inorganic contaminants, IOCs, they produce biofilm response and prevent their entry into their cellular matrix or cytoplasm. So the next mechanism is siderophore. So siderophore is a normal process, production of siderophore, and siderophore is an ion complexing low molecular weight compound, organic compound, and this compound complexes the ion so that it is transported across, as you can see in this diagram, it is transported across your membrane, and it is used for its metabolism. So here it works in the opposite way. So it binds to the, it releases siderophore, the cell releases siderophore, and it forms a siderophore metal complex, and it takes it away from the cell. So when this particular, it is not dependent on, usually siderophores are produced to complex ions, that is Fe2 plus and Fe3 plus. But in cases, since aluminum, gallium and chromium have very similar chemistry to that of the Fe3 plus ions, they can be used interchangeably. So when the cell faces aluminum toxicity or gallium toxicity or chromium toxicity, they produce siderophore in response, and the siderophores attach to the Al3 plus ions or chromium 3 plus ions and make it less available to the cell and takes it away from the cell. So that is one way where they work from preventing the metal from entering into the cytoplasm. So the last method is biosurfactants. So biosurfactants are a class of compounds. Again, there are some kind of sulfates which I'm not really sure about, but these class of compounds are secreted by microorganisms, and they're good emulsifiers, and this particular emulsification complexation process increases the solubility of metals. So metals are not readily soluble in nature, but when biosurfactants are produced, they complex the metal and again stop it from diffusing into the plasma membrane. So as you can see, a bacterial cell, in response to the heavy metal toxicity, produces biosurfactant, and this particular uh, inorganic metal, whatever metal it is taken up by this biosurfactant, produced in a micelle-like structure and taken away out of the area. It is taken away from the area of the microbial cell. So these mechanisms are completely metal independent. It works for any metal, whether it be cadmium, whether it be zinc, whether it be lead, whether it be mercury. It works for most of the metals, and it is not specific at all. So what are the specific mechanisms? What are the metal dependent mechanisms? So we have three main. As I said before, there are many metal dependent mechanisms, but some of the few which we commonly represent are metal efflux systems, sequestration by metallothioneins, and methylation. Okay, so these are also sometimes energy dependent. So metal efflux systems are basically ATP synthase in pumps. So in electron transport chain, you have an ATP synthase, and we know that there is a chemiosmotic potential, and the H plus ion concentration is used to make generate ATPs. So they use the same concept here. We have ATPase pumps, and these pumps pump the toxic ions out of the cell. So while in some cases where the metals are lipid soluble or they can be actively transported inside the cell, these pumps again spend energy to remove them by creating a chemiosmotic potential and pump them back out of the cell from the cellular matrix. So they are energy dependent, and they are efflux systems which remove metals out of the cell. So the next process is sequestration by metallothioneins, and metallothioneins are again low molecular weight cysteine-rich proteins, and these proteins are very specific to cadmium. So these proteins are present inside the cellular matrix, and once the cadmium is transported across the plasma membrane into the cytoplasm, this induces the production of metallothioneins. Metallothioneins are not always present inside the cellular matrix, but they are produced in response once the cadmium enters the cell. So once it enters, it binds, the metallothionein binds the cadmium and accumulates in a particular region near the plasma membrane inside the cytoplasm. So when you use TEM, usually we use TEM to learn about metal accumulations inside the cell. So when we use transmission electron microscopy, these cadmium accumulations surrounded by metallothioneins, which are cysteine-rich proteins, so you can see them as electron-rich areas. So you can see in TEM these areas which are very darkly colored and which are present as accumulates or aggregates inside the cytoplasm. So the third method is methylation, which is very simple. It is the addition of methyl ethyl group. So why they actually add methyl and ethyl group is to reduce the toxicity and increase the metal volatility. So certain elements, especially mercury, when they are present as elemental mercury, they are very toxic in nature, and when they are converted to other organic forms, they increase their own metal volatility. So volatility is their capacity to change from liquid or solid phase to gaseous phase, to change into vapor. So when some metals, some elements, especially mercury, when they are when methyl and ethyl groups are added, they change and they increase their volatile nature. They become more vaporized easily. So this vaporization increases uh, uh, sometimes increases metal toxicity, but mostly as soon as this particular mercury is volatile, the ratio of how much enters the cell is greatly reduced. So that is how they usually decrease their metal toxicity. So once mercury becomes vaporized, not much is left to diffuse into the cell. So that is how methylation actually helps the cell to deal with mercury resistance. Okay, so this is yet again a very good illustration of the different mechanisms. You can see flux pumps, and you can see enzymatic conversions, and of course you can see metallothionein chaperones, and you can see sequestrations by EPs. Okay, so let's go to the next. Okay, to summarize, so we have seen different things along this presentation. We've seen the difference between biodegradation and remediation, and we have seen what are the different components involved in bioremediation. We have discussed how a microorganism interacts with the organic pollutants, inorganic pollutants, how they interact in normal conditions to these substrates with different types of pollutants and contaminants, different types of mechanisms of how a cell deals with organic pollutants and how they deal with the metal toxicity. So this covers the first part 1 of bioremediation. So in part 2, we will be dealing with how these techniques are taken ex situ and in situ, and what are the different techniques that we use in our treatment plants to effectively clean up a polluted site. So that we'll deal with in part 2. And here many of the illustrations are from the World Wide Web, and used different illustrations from textbooks also. So one of the major textbooks that I have referred, and which is a very actively suggested reading material, is the Ian Pepper, Environmental Microbiology. So all the resources, all your reading materials along will be uploaded, and your worksheet will be uploaded along with this presentation to your groups and to your classrooms. So I hope that you use the worksheets to work it out, and make use of this as much as possible. So thank